All right. Don't know what happened there, but anyways, right. I promise you, you have the ability to get a better grade on a problem if you write something down than if you put nothing. I promise you, you can't do worse than 0, and you will get a 0 on a problem if you put nothing down. Okay, so put something down, write whatever you think might be relevant. You can earn point, you know, like if you understand what are the right equations to use, that can earn you some points, right? And other things, right? So again, just attempt every problem to the best of your ability. Okay. If there is a part B that relies on an answer from part A and you got no clue how to do part A, just assume something. Okay, just pick a number whatever you want for part A and use that to do part B, and you will still earn full credit for part B. I will not dock you just because you can't do part A in a problem, right? So if one answer relies on another one, if the first answer is wrong, you can still earn full credit for that second answer. Okay, right? So again, I say all this to continue to stress the idea that you should try and work on every problem as best as you can. Okay. Okay. Audio. All right. All right. Thank you. I don't know. Audio without people. Okay. Let me change the chat settings. Sorry, I didn't really Zoom save chat settings between sessions. I had the chat set to only being able to have private messages with me because I had an exam with some people on Zoom for general chemistry on Wednesday. So, yeah. Anyway, thank you for letting me know about the audio. I have no idea when exactly that came out. Basically, I was just saying, write the exam. Okay, yeah, so the exam 75 minutes. You will be given some equations and things on the exam, and you don't have any extra notes you can bring to the exam. So Samantha, there will be no note cards for the exam. Okay, right? But we'll talk in just a minute about what equations will be given on the exam, and then what equations you're expected to know. Okay, and you're expected to know when you use said equations. Right, yeah, 75 minutes. I guess for those taking the exam over Zoom, okay, right, those are taking the class online, not coming in for the exam, right, you need to consider making sure you have a setup so that I can see your computer screen at the same time as you're taking the exam. So, right, I guess like if let me see what the heck one can see here, right? So, you'd have to have, the camera set up so I could see like this in your work area, right? So something kind of zooming out, right? If you look at my screen, I guess what I'm displaying right now. Right, this thing, right, to be able to kind of see where you're working as well as the computer screen that you're working on, right? So you'll need to log into Zoom and have that kind of displayed. Okay. I will be here before the class starts, 15 minutes, to help those who are on Zoom to get set up, make sure they're good to go before the exam starts. You're taking the exam again online. The exam will be available to you over Canvas. And you will take the exam on Canvas, and you'll need to upload your work. At the end, there will be a question that has the ability to upload your work. And so, yeah, so you need to upload your work in order to receive any type of partial credit on a problem, right? So just make sure you do that, okay, when taking the exam. You have the same amount of time as everyone else, and you're taking the exam at the same time as everyone else in person, okay? Yeah, so other questions people have about the exam, whether it be for taking in class or online, or just any questions in general about how it will work, how it will run. All right. So a couple of notes about when taking the exam, right? One, make sure you're keeping track of your units, right? Whether or not things are in joules versus kilojoules, things like that, right? Because that can mess up your answer and can lose you some points. So just keep track of units in the problem. Make sure you know what your units are and that you have the correct units and are converting when you need to convert. Right, if you get a final answer and it's just way off, like you get an answer and your pressure is negative, okay, right, you can at least earn an extra point if you at least tell me, hey, I know something went wrong somewhere. I cannot have a negative pressure. That is not physically possible, right? Okay. Otherwise, if you have just some answer that makes 0 sense and you move on, right, then that's, you'll just be able to earn some extra points for that answer. Right, and I already talked about if you can't do part B, A, assume something for it to do part B, right? And then just as a note, there are tables given on the exam, okay? These tables, right, have some form like this, right? It'll say like molecule H2, and then it'll have like, say, the expansion coefficient alpha divided by 10 minus 4, Kelvin to the minus 1, it's 1.35, okay? This notation in the table is telling you that alpha equals 1.35 times 10 to the minus 4 inverse Kelvin, right? So alpha for H2 is 0.00035 inverse Kelvin, okay? It's divided by 10 to the minus 4 is indicating that this number here was divided by 10 to the minus 4. So the true value of alpha, you have to multiply it by 10 to the minus 4. So, right, alpha for H2 would be 1.35 times 10 to the minus 4 inverse Kelvin, right? Okay. Just keep that in mind, those type of notations on tables. Yeah. I typically try to indicate what units I'm searching for the answer. I can't guarantee that's every time. I will say that, I'm not too picky about whether or not your units are exactly what are asked for, as long as your number is correct with those units. But I appreciate it because it makes it easier for me to grade. If everyone's answers in the same units, then all the correct answers will be roughly the same number, right? Now if it's joules versus kilojoules, it's pretty easy to convert and figure out whatever, right? But if you have a pressure and you decide to express it in terms of PSI or something like that, it's going to be annoying for me to convert and whatnot. And so if you have the right answer, you have the right answer, and that's fine. But I do prefer the units that are kind of given and asked for in the problem. But I can't guarantee every time they'll specify specifically this unit. I try to make sure to say that, but but if I don't, it's just don't worry too much about it. As long as you feel confident that the unit you have is correct with the number that you have, right? That you didn't calculate liters to atmospheres and just write units of joules. This is a very common thing to do for people to calculate. They do pressure times volume, they get some number, and they say that's what it is in joules. And that's not what it is in joules. The units are liters atmosphere, and you have to convert that to joules. Okay. Other questions? I don't care about significant figures, by the way, significant digits or whatever, right? Be reasonable, okay? Don't write out 10 decimal points. Don't also round your number, you know, like don't round 1,823 to 2,000, right? So you know, just be kind of reasonable. Anything else? All right. So equations should know, right? There are different equations that have popped up throughout the semester so far, right? Ideal gas law, hopefully we know that from Gen Chem. First law of thermodynamics, should definitely remember what that is. Conservation of energy, right? The relationship between CV and CP for an ideal gas. Kirchhoff's law, I think I said that right. Could have pronounced it wrong, but anyways, right? How enthalpy reaction changes with the change in temperature. Okay. Right. And you know, and then what the heck is delta CP here? Well, it's just this formula here, right? And that delta CP formula is the same type of formula as the enthalpy change of a reaction, written in terms of enthalpy formations of reactants and products, right? So those two formulas are essentially identical. Just replace delta H with CP, and you got the exact same thing, right? The definition of your compression factor, right? Some basic ideas of mixtures of gases, right? Total pressure is sum of partial pressures, right? Partial pressure of a gas is just the total pressure times its mole fraction, okay? Right? And then for ideal gas, right? For some chemical reaction or phase change, enthalpy is related with the change in internal energy plus RT times the change in number of moles of the gas. Okay? These slides are also posted online as well. Should be there already. I'll double check that after class, but they should be there already. Right. And then the other equations, right, I kind of put in this table as we'll fill out throughout the semester, right? Calculate work, heat, internal energy, enthalpy, right, for different types of problems. Right. So all of these are assuming a constant heat capacity, and they're assuming we're expanding or compressing a gas, right? No phase changes, no chemical reaction, okay? Right? And in those cases, right, we have, you know, these different ways of calculating work. Really, there's, you know, two different ways, the reversible isothermal or constant pressure. Otherwise, it's just the first law of thermodynamics to get work for, say, like an adiabatic case, right? Heat, basically use the first law of thermodynamics, right? Internal energy, CV delta T, right? Enthalpy, CP delta T, right? So while there looks like there are a lot of equations on here, there's a total of really five unique equations. First law of thermodynamics, which we talked about in the previous slide, for constant temperature and for a constant pressure, and then the expression for delta U and delta H. Okay. All right. And then some, for example, equations will be given, right? The definitions of these internal pressures, expansion coefficients, so on and so forth. The exact relationship between CP and CV for any gas, right? So if you don't want to memorize the relationship between CP and CV for an ideal gas, you could always calculate it here, right? Remembering that alpha for an ideal gas is 1 over temperature, 1 over temperature, and kappa sub T is 1 over pressure, right? And you have your temperature changes and pressure changes for an adiabatic reversible change in state. You have your Van der Waals equation of state and your Viral equations of state. Okay? Real gas. I think that's, yeah. So these are the equations given. There will be a bunch of stuff given at the front of the exam because not only will I give equations, I give different things, right? Like we potentially can have information, enthalpy of reactions. So there'll be a table of enthalpy of formations given in the exam, right? There will be a table of heat capacities given in the exam. I don't know, and a bunch of other stuff, right? Some constants, right? R, right? Gas constant, and other things like that are given. Okay, tables like coefficients and isothermal compressibilities and all that wonderful stuff. So there will be a bunch of information given in the front of the exam. Okay, you will definitely not use all that information throughout the entire exam. Okay, but a question might involve that, right? So if you have a question and it doesn't say what the heat capacity is for your gas, most likely you got to look it up at the front of the exam. Okay, you have a question that uses the expansion coefficient of some liquid or solid, most likely it's given in the table in front of the exam. Okay, so just keep that in mind, that some information for some of the problems might exist in tables near the front of the exam. Okay, and won't all necessarily be given within a given problem. Okay. All right, so questions about equations you should know, given equations, things like that, what you need to know for the test, right? Could be worse. People used to have to derive all these equations on the exam. So, you know, I'm not doing that to you. But yeah, no questions about the exam itself, structure of it. Okay. Huh? Yeah, 4 kind of free response questions, more or less. Might be 5, I don't know. I'm still finalizing it. And again, each question could potentially have multiple parts and stuff. You know, so it just depends. I usually start off with more questions than is reasonable, and then I trim it down from there to figure out kind of the final number of questions that can be, you know, that is reasonable to do in the given period of time, right? But, you know, before this exam, I take the exam myself and take the time it takes me to answer the questions and multiply it by some factor to determine whether or not I feel, you know, the class in general can finish the exam in a reasonable time. So, okay. Yeah, so I don't know the number of questions exactly. So, but we've covered a lot of stuff, right? So it won't necessarily be that every single concept and every single type of problem will be on the exam, right? Because we have a lot of different homework problems, right, that say we've done, right? And each homework has like 10 or more different problems, right? Some of them are related, a lot of them are very different, right? And so there's no way every type of problem is going to be on the exam. But you don't know which ones will be, okay? But I will say, right, that the types of problems that are on the homework are very comparable to types of problems that would be on the exam, minus those that require like some, you know, extra math stuff and looking up like how to solve a problem, like an integral or something like that, potentially online, right? Like in terms of math level, it's always simpler math on the exam compared to what potentially can be on the homework. Okay, so yeah. All right. Anything else? All right. So are questions that people would like to review, go over, talk about? I won't necessarily do homework questions because people haven't handed in their homework. They're in person or online. So I don't want to necessarily answer a homework question in class when people can answer that question. Now I could do a question similar to a homework question, and that's fine. But I don't want to necessarily do the exact homework question. Yeah, so if people have specific things they'd like to see, happy to do it. Otherwise, I have a bunch of different questions thrown up here, right? And we could cover whatever questions we want whenever we want, right? Yeah. But first, start off to see if there's something someone would like to see first.
Could you explain like why the work done in a reversible process is always more than the work
So I work for reversible is always done greater than for an irreversible. Yeah, I mean, so kind of the easiest way to think of this and see this is, right, let's think about, right, a piston, right? So just to make sure for those who are on Zoom, everything, right? The question was, is why is work reversible, right, always greater than, right, or potentially equal to work irreversible? Now, it's typically, basically, it's going to be greater. The only time it's equal is if they're both actually done reversibly. But yeah, so I'll just say greater than, right? The reversible work is always greater than the irreversible work. Oh, that is really focused here. All right, that's better. Yep. Right, so why is this the case? Okay. So let's think of, say, compressing a gas. Okay. Let's say my gas originally here is at 1 atmospheres. Okay. And I want to compress the gas down to, say, 5 atmospheres. Right? So let's say we're doing this, okay? If I want to do this irreversibly, right? If I want to do this thing irreversibly, right, I would take my container that's at 1 atmospheres, and then if I did it irreversibly, I'd say just apply, okay? I'd apply 5 atmospheres worth of pressure on my container, right? Until it gets compressed down to 5 atmospheres, right? And reaches essentially mechanical equilibrium, right? So that's how I would do this thing irreversibly, right? This is irreversible, okay? Right? And so when I'm doing that, right, I really should have done this for an expansion, make it easier. And then if I want to do this reversibly, what I'm doing, right, instead is I have 1 atmosphere here, right? I apply a pressure of, say, like 1.1 atmosphere, right? And then I apply, you know, and it went down a little bit, and I apply a pressure of 1.2 atmospheres. And then I apply pressure of, you know, 1.3 ATM, and so on and so forth, right? So eventually I've gotten to a place where I've applied 5 atmospheres worth of pressure, right? And this would have 1.2 inside. This should be 1.1 then, 1.3, right? So I'm slowly increasing the pressure of my gas and slowly increasing the external pressure applied to my gas, right, in this piston, okay? Right? And so, right, in terms of compressing the gas, right, the surroundings is doing the work, right? Well, when I compress my gas irreversibly, right, if I imagine I do this thing very quickly, right, and I just want to compress my gas till it reaches the volume that it needs to be at for the pressure to be 5 atmospheres, right? So I do this compression very fast, okay, right? Right? You can imagine you do it quick enough that when you're compressing the gas, you're pushing against basically 1 atmosphere worth of pressure during that compression, because, you know, you're doing it so quick that you can think of doing it so fast that the gas molecules don't have time to heat up or cool down or whatever they need to do, right, to you know, have this increase in pressure, right? And so the pressure that I'm pushing against is still roughly this 1 atmosphere worth of pressure, right, until I get down to, I reach equilibrium and things equilibrate, and I'm left at 5 atmospheres here, right? While here, when I'm compressing my gas, the pressure inside my container is slowly increasing as I compress the gas. And so I'm pushing against more and more pressure as I'm trying to compress the gas. So it's going to take more and more work to do so. The expansion is a little bit easier to kind of see because in terms of like irreversible, right? If I want to expand, if I want to do the other way, right? I start off with 5 atmospheres worth of pressure, right? I then change that, you know, remove some weight or whatever, right? Change it to 1 atmosphere worth of pressure, right? As I go from left or right to left, okay? And then my gas is expanding against just 1 atmosphere worth of pressure, right? So it takes us work to push against that 1 atmosphere worth of pressure. But if I go right to left for the reversible case, right, I'm expanding against 5 atmospheres of pressure, then 4.9, then 4.8, and so on and so forth, right? So I'm expanding against more pressure for the reversible case than the irreversible case, and so it's going to require more work. And so that's basically why the irreversible expansion compression is always less work than the reversible. It's because the pressure that it's expanding or compressing against is always less than for the irreversible case than it is for the reversible case. Okay, they might equal at one of the ends, but they aren't the same, right? We had the plot of like pressure versus volume, some change in volume, right? Constant pressure, you know, a constant pressure expansion looked like this, while say the reversible case looks something like this, right? We had this extra work that's done because of the fact that you have to expand against a greater pressure at some point during the expansion, right? And why the pressure has to be greater here is because to do this reversibly, right, the pressure in my system and externally have to be the same, and the pressure of your gas is not going to be constant during this change in volume, right? And so that changing in internal pressure is reflected by the change in external pressure for reversible expansion, causes then more work to be done. Other questions we'll have? Yeah.
So is it like for irreversible work is done in one step, and reversible work is done in every step?
Yeah, now you could do an irreversible process in multiple steps, but a reversible process has to be done in these like infinitesimally small steps, like almost an infinite number of steps. To do something perfectly reversible, you have to, yeah, essentially be doing like an infinite number of steps to go from the initial to final state, because you have to maintain equilibrium every time. And if you do too large of a change on your system abruptly, it's not going to be at equilibrium, right? In our case, mechanical equilibrium, right? When you think of compression or expansion of a gas, right? And if you apply too much pressure, too much force on your, say, piston at once, then the pressure inside and outside are not going to be the same during that expansion or compression. And so you're not in equilibrium, and that's not going to be a reversible process. So yeah, so you need to do things right in almost an infinite number of steps if you're doing it reversibly versus irreversibly. You're doing something in a finite number of steps, and you're making more abrupt changes to your system and surroundings, which causes it not to be able to be restored. Okay? Right, and this this will have a lot. We'll talk a lot more about reversible and irreversible. We'll talk more about entropy, because things being reversible and irreversible is related to certain ideas of spontaneity and entropy of your system and surroundings and how they're related. Okay, so there's a lot more to kind of consequences of doing things reversibly versus irreversibly than what we've gotten to. Okay, but right, but in general, a reversible change in state is kind of an ideal case. We can get close to doing things reversibly, right? We can get roughly close enough, but to do things perfectly reversibly, it would take an infinite amount of time. We try to get to as close as we can, because again, that'll give us the most efficient thing, right? We'll talk about when we talk about entropy, we'll also talk about efficiencies of like heat engines and things like that, right? And if you want to get the most efficient amount of work done from a heat engine, you want to do things reversibly, amongst some other factors as well. Okay. Other questions about this or something completely different? So this is a very quick question. I forgot to change that from clicker. We're not doing clickers this semester, right? But simple question here, right? Which of these constants, internal pressure, expansion coefficient, Joule-Thomson coefficient, or isothermal compressibility, tells me how much the volume changes when I change the temperature of a substance at constant pressure? Yeah, it'd be the expansion coefficient, right? It's a change in volume, expect a change in temperature at constant pressure. Okay? Right? Right, and that type of identification is something that potentially is needed in a given problem, right? Because a problem isn't necessarily going to be laid out, right? On homework and on exams, problems tend to be tried to be laid out in ways that you might encounter, in real life, in a lab or something like that, right? So, right, in a lab, you're not going to have something that's saying, oh, use the expansion coefficient to solve this issue you have in the lab, right? It would be, right, in lab, you're like, okay, I want to know for this material, how its volume changes with temperature, okay? And I want to identify, okay, well, what property of that material is related to that change in volume with respect to change in temperature at constant pressure, and that would be the expansion coefficient, right? So being able to identify, right, what's happening in a problem versus what things are relevant to that problem, right, it is kind of a key step, okay? And so, this question is just kind of getting at that, right? If you had some problem that's said, I have, right, like the example problems we did last time in class, I think it was last time, right? Right? Right, where if I expand, I heat up some solid at some temp, at some constant pressure, right? What's the percent change in volume, or what's the change in volume, right? We had to use the expansion coefficient to solve that, right? And the problem didn't say use the expansion coefficient to solve this, right? But you need to know that what's going on in the problem is related to the expansion coefficient, and that would be useful to help solve the problem. Next question?
Yeah. It was in the homework. It won't be like an answer to the homework, but I guess on problem 10, it had you solve for the change in for the internal energy, or like the molar internal energy. It is isothermal. Is it only equal to 0 if it's an ideal gas or non-ideal?
Yeah.
Okay.
Yeah. For an ideal gas, I wonder if I have.
That's just because the internal pressure is also equal to 0. So
Yeah.
Isothermal.
Yeah, I sub T is pressure is equal to 0 for an ideal gas. And don't know if that question like that here. John's law question. Nope. Okay. So I don't have something like that here, but yeah, that's essentially using this pi sub T, right? And the fact that your change in internal energy is related with this internal pressure times your change in volume. Great. Other questions? Right. So we'll just kind of do this question here, right? I have 0.35 moles of an ideal gas that I reversibly and isothermally compress from a volume of 13.2 liters, 0.8 liters at a temperature of 325 Kelvin. Question is, what is the change in internal energy, change in enthalpy, heat transferred, and work done for this process? All right. So in this problem, right, it's an isothermal. It's done reversibly. Okay. So we know it's a reversible isothermal change in state, right? I wrote down some of the relevant numbers, right? What are the relevant equations I could potentially use, right? For work, how would I potentially get work for a reversible isothermal process? All right. How would I get, say, delta U? So it'll be 0, right? CV, delta T, right? Delta H, CP, delta T. Okay. Now the problem, the CVs and CPs weren't given in the exam, right? If they're not given, doesn't mean that I forgot to give them. It means that they're going to be in a table in the front of the exam. Now here, I didn't give them. They're in a no table, but it's because they're irrelevant. Because change in temperature, right, is 0. Okay, right. And then, right, to get Q, yeah, right, Q, we would use the fact that delta U is equal to Q plus W, and so Q equals minus W, okay? So for example, in a problem like this, let's say this was a test question, okay? Right, I've calculated nothing so far. I guess you could say I calculated, well, let's pretend I didn't write down that these are equal to 0, right? All right, I've calculated nothing for this problem, right? I just wrote down the information given and wrote down relevant equations, okay? This already is going to earn you, like, you know, if this problem say worth like 8 points, this is potentially 50% of the problem, right? Just identifying what are the correct relevant equations needed to solve for the things we care about, okay? And what is going on in the problem, right? That it's isothermal, reversible. That means you got to use this, right? Delta U, delta H are related with this, right? Q I can get through this, right? And then again, this is already going to be, you know, potentially 50% of the show of the points in the problem just here, okay? Just to give you an idea, right, of how I'm weighting and grading these things, right? It's not going to be the majority of points are, can I plug into this equation here and calculate the correct value of work? No, that will be some points, right? But it's not going to be, you know, 80% of the problem. Okay, it's going to be closer to 20% of the problem. Okay, so right, so delta U and delta H are equal to 0 because delta T is equal to 0, right? And Q is then equal to minus work because of that. Okay, so all we got to calculate is work here, right? Which is a minus 0.35 times 8.314 times 325 times the natural log of 0.8 over 13.2. Yeah. Right, so that's just plugging in all that stuff, right? Which gives you a work of 2.65 kilojoules. Okay? And then heat then is just minus 2.65 kilojoules. Okay? Right. Again, I mentioned this at the very beginning of the class, right? Not class day, but like class, right? At the beginning of the semester, okay? And I keep on trying to emphasize this, right? That what we're concerned about in this class is not can you do the math, not can you plug into minus nRT ln final over V initial and get 2.65 kilojoules, right? That's great if you can. I mean, it's expected you're able to do it, but that's stuff you should be able to do before you start this class, right? What we care about and what I care about in this class is given a problem, right, given some situation, can I identify how I can calculate the relevant thermodynamic quantities for this problem, right, for this situation, right? Setting up those equations, right, how would I get work, right? What's going on in the problem? What does that tell me about how I might be able to calculate work and heat and this and that, right? That is the most relevant thing, right? That's what, you know, I hope we take away from this class, not can I plug into the equation of work NRT, V final, and V initial to get a number, right? That's not what I'm concerned about you learning from this class, because that's not something you should learn from this class, because you should already know how to plug into an equation to get some number, right? Okay. So again, that's why, I emphasize, if you're one to try to optimally use your time in some way to study for the exam, right? You can go through and work through every problem, plug in the numbers and things like that, and that's good and that's great, right? But if you're limited on time, right, then just try to at least set up every problem, okay? Right? Try to start with setting up the problems and seeing if you potentially set it up correctly. Go through questions on lecture slides, okay, where I have in more detailed answers, right? I know the homework I don't have very detailed answers, but lecture slides I do. Trying to remember. On Canvas, I don't have any like solutions to problems in the book on Canvas, right? I think I only have those available for my Gen Chem class, but I can't remember this class. Let me see here. No. Okay. Yeah, as I said, I don't think I'm allowed to share solutions to the book problems. Otherwise, I would have. But okay. Right. And again, there's only so many ways I can ask, say a question like this. Firstly, isothermally expanding gas, okay? Right? So there's a good chance that one or two questions that pop up, say in the lecture or on the homework, are going to be nearly identical to a question on the exam. Because again, there's only so many ways I can ask to do the same thing, right?
Good question. So let's say we wanted to use negative external delta V in the ideal and reversible. We just calculate the pressure for volume changes.
Well, so for this, if you tried using minus P external delta V, you could try to calculate the pressure, but the problem is the pressure changes initially and finally, because this thing's done reversibly, so the pressure externally and internally are both changing. And so you won't be able to find like what pressure to use, because P external is not a constant number. It's a varying number, which is why we end up needing to use that minus NRTL and V final over V initial, is that we get that through how the pressure is varying with the volume. Right. Yeah. Yeah. Okay. Other questions? Right, and we did a lot of examples of these types of expansion compressions and going over the equations, right? In a review we kind of did last week, I think, right? I guess I could post the updated lecture notes that have those questions in them, but I don't think I ever typed up the actual, like, relevant equations, but you can always look at the lecture videos online as well. Okay. All right. All right. So here we have the adiabatic reversible expansion of 0.02 moles of argon, initially at 25 degrees Celsius, from 0.5, 1 liter. The molar heat capacity is 1.5 R. Right. What is that final temperature of work? Delta U, delta H, and Q. Now for this problem, you have to look up the how T final you get from T initial, so you don't remember that. That's fine. But again, at least think about how you'd set up this problem, even if you don't remember exactly all the equations. So we'll just kind of did last problem first. Talk about how to solve things. Right. So I have this reversible adiabatic expansion. Okay. And I'm wondering again, what is work, internal energy, enthalpy, heat, things like that. Right. This problem is specifically asked also what is the final temperature. Okay. Right. And for this, the final temperature, right, you'd be able to look up that relationship equals the initial temperature times the, let's see here, is it initial volume, I think, over final volume to the R over CV. I believe it's that equation. I think so. Right, let's see here. So my initial volume is right here. I'm expanding my gas. So this number is going to be less than 1. So a smaller number, just saying that the temperature should go down. And when I expand the gas adiabatically, reversibly, the temperature should go down. Yeah, so that's the right ratio, initial over final, right? Again, when looking at these problems, right, you can do kind of what I did. Now, you don't have to remember this equation off the top of your head, but you should be able to at least have an idea of what some of your answers should look like, right? So, when I'm thinking and going through the problem, right, do I expect my final temperature to be less than or greater than my initial temperature? Less than, right? I should expect the temperature to decrease because for an adiabatic reversible expansion, right, adiabatic means Q equals 0, right? So no heat is being transferred. If I expand my gas, that means my system is doing work. It's giving up energy to do so, right? It's giving up some of its internal energy to do so, right? And so if it's giving up some of its energy to do that, right, I have an ideal gas, its only energy is kinetic. Its kinetic energy has to decrease. With a decrease in kinetic energy, that corresponds to a decrease in temperature, right? So the temperature has to go down for an adiabatic expansion that's done reversibly, okay? Or irreversibly, I guess, in that matter, right? That temperature will decrease no matter what because it's adiabatic, right? An adiabatic expansion, the decrease in temperature, okay? Right, so I should expect my temperature to be less than my initial temperature, right? Right, I should expect work to be, less than 0 because, again, my gas is expanding, right? It's doing the work, right? I expect my internal energy to be less than 0, okay? And then enthalpy, I'd also expect to be less than 0. I mean, that's maybe not as obvious as to what to expect, but given what the formula is, we'll see, right? But so anyway, so how we would calculate work using what for this? Yeah, right. It's related with the internal energy because the first law of thermodynamics, right? Right. In every one of these problems, you can write down the first law of thermodynamics as an equation that's given, right? Because the first law of thermodynamics always works, right? For any expansion compression of the gas, I always know delta U is equal to Q plus W, right? In this case, Q is 0, so delta U equals Q. Delta U, I always know, is, here I'm going to use NCVM, delta T, because they give us the molar heat capacity. Okay. Oh, that's it. It should be a CV, right? And then delta H, right, is just NCPM delta T. Okay. And these are my equations that I need to solve, right? I first need to solve for that final temperature so I can get my change in temperature and then solve for these guys, right? Now CP for an ideal gas, right? CV plus R or NR, right? Or CPM, right? And CVM is just equal, CPM is just CVM plus R, okay? Right. So it would be 5/2 R, right, for this. So questions about kind of what the relevant equations are for this problem, how we set it up, how we go about solving it. just remind you on exams, right, there are these wonderful good faith points. So again, roughly half the points of the problem are typically involved in just this step here, right? And what we got here, roughly half the points of the problem is going to be allocated, right? Which I know then says, well, I guess score 50% on the exam. That's a failed grade, but not so, because you can, there's this built-in wonderful good faith points, 20% essentially. So that is a passing grade, right? So even if you don't know how to plug in and do anything else from this point on, right, still potentially be able to pass the class. Because again, I'm just emphasizing, right, because that is what we care about in this class, right, to at least be able to pass and proceed through this class. We want to be able to understand, how do I set up, right, this stuff, right? I'm given some situation. How do I calculate these things that are relevant to that situation, right? That is what we're trying to make sure we emphasize, what we understand in this course, okay? All right. So again, just kind of some of the information given, right? Here I calculate pressures, not really that relevant, the pressure, but calculate all the same, right? So we calculate the temperature using this equation here, okay? Right, T initial times V initial over V final, R divided by CVM, okay? Right, which plugging in for those things gives you 187.82 Kelvin, okay? Right, the change in internal energy is the same, right? Work is equal to change in internal energy, which is N CVM delta T. Okay, so work and delta U are equal to each other, and plugging in for that change in temperature, the heat capacity at constant volume, okay, and the number of moles gives you minus 27.51 joules. And then CPM, right, you just do 5/2 R, right, and that's what your enthalpy change is, and then Q has to be 0. Okay. Questions about this problem? Right. Yeah, so here, right, so let's just, well, let's not spend too much time going over this problem, but let's just, right, so this is the stuff that's relevant for a reversible adiabatic expansion, okay? What about if I do the same exact process, but do it irreversibly at a constant external pressure, okay? Adiabatically, right? That's what's in that in the problem is saying, now I'm doing this change of state irreversibly constant external pressure adiabatically, okay? All right. And so the question is what's different? What's the same, right? What can I use from here to here? What is different to get to what I need to do, right? Right, Q exactly still 0, right? It's the same, which means work still equal to delta U, and we know delta U is still equal to NCVM delta T. We know delta H is still equal to NCPM delta T, because these two things are state functions. So I can always use those equations as long as I have no chemical reactions or phase changes. Those equations work perfectly, right? For constant heat capacities, okay? Which again, unless a problem specifically says the heat capacity cannot be treated as a constant, you treat it as a constant, okay? You will be told not to treat it as a constant in the only cases where you need not to do so, okay? So even though, right, one of the tables in the exam will be some heat capacity equations, if you will, right, a table related with some non-constant heat capacity for different gases, okay? The only time you need to use that table is if in the problem it says to treat your heat capacity not as constant, okay? Right, there will be two heat capacity tables, one for constant heat capacities, one for non-constant heat capacities, right? Again, never use the non-constant heat capacity unless you're told to do so, okay? All right, so back to the problem, right? So great, so I have these kind of equations what other equation do I have now for this problem that I didn't have before? Yeah, minus P external delta V for my work, right? Because it's a constant external pressure expansion. So I know work is minus P external delta V, okay? Right? And so that is, right, and so I can calculate minus P external delta V because I'm given my change in volumes, I'm given the external pressure. I can use that to get the change in temperature, right? Which then I can use to solve for the final temperature if I want it, as well as then the enthalpy change. Okay? Yeah.
You not use that the T final equation before?
Yeah. So this does not work for an irreversible constant external pressure adiabatic expansion. This is only for adiabatic and reversible. That would be both reversible and adiabatic, right? Because we got that equation by assuming the pressure, right? Basically, we got that equation because we said, okay, dW equals du, because it's adiabatic, which is P minus P external dV equals CV dt, okay? And then we said, okay, if it's reversible, that means P equals P external. And if it's an ideal gas, that means P equals nRT over V. And so then I take this equation and I get minus nRT over V dV equals CV dt. Oops. Right? And then I integrate this equation out and you get this formula here. Right? When you integrate out that equation in terms of dV and dTs and such, it'll simplify to this formula here, right? And so to get this, I had to assume an ideal gas and I had to assume a reversible process. Thank you. And so that again, that's part of the reason why in the lecture videos online, and I highlight some of it in class as well for different times, right? But why the notes and the videos and things like that in the book, right, go over how we get to, say, these equations, right? Because there are certain assumptions that are typically made to derive some of these equations, right? And so, right, sometimes seeing, right, how it's derived and saying, okay, right, I had to take this step here to get to my final process, right? Because if you integrate this, you'll get something that you'll have ln and T final over T initial, right? So minus n R over CV, and this will be ln V final over V initial, right? And you integrate that out, right? So, okay. And yeah, so right. So the derivation required these assumptions, okay? And so, you know, I mean, not for everyone, but for some people, right, it helps to see those derivations and see, okay, these were the assumptions had to make to derive that and how they were made and why they were made to make the answers work out the way they do, right? To then be able to remember, okay, this only works for an adiabatic reversible expansion. Okay? Yeah, which I guess is something, right, in the equations that are given, right, they're given, but they're not necessarily always told what they're for, right? So you still need to understand, even with the given equations, right, to be able to recognize, oh, that's for this, right? That's for an adiabatic reversible expansion, okay, right? That is, you know, only used in these type of problems, okay? Right? Which is one of the reasons why note cards aren't kind of allowed for this exam, because then you can just write all that stuff down for the exam, right? You could say, okay, if the problem says this, do this. If it says this, do this. If it says this, do this, right? And then that's basically the exam, right? That's what I want, you know, what you're supposed to be able to do on your own without having to look up in a note card or in a textbook, right? Is the idea for this class, right? To be able to identify, right, what's happening and what I can use to solve for something I need to solve for, right? Right. Now it feels like I'm kind of beating the same drum over and over again, but yeah. All right. But here, we have a problem involving a phase change, okay, where I'm blowing off 100 milliliters of water, okay, and I want to know what these different thermodynamic quantities are given the enthalpy of vaporization of water at its boiling temperature of 100 degrees Celsius, right, or 300. Oh, you know what? This problem was grabbed before, and I did not fix that. Shoot. Where the heck? I don't see it. Yeah, I think we'll do here. So let's just talk about this real quick. I just kind of looked at the time. There's at least one other problem I want to get to. We'll kind of talk about this problem together, right? So right here, I have a phase change. I'm going to write down some of this information. Okay. Position 2, 5 mole. Okay. All right. So again, we have kind of this rough problem, right? Now we're also given like the density and the volume and blah, 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 but I didn't bother kind of writing that down real quick, but right. But the question is, right, how would we get these thermodynamic quantities, right, for a phase change here, okay? So if I'm looking at the enthalpy change, how would I get the enthalpy change for this phase change? Yeah, remember moles times the enthalpy of vaporization, right? Which is a molar quantity, okay? And I get the moles, right, from the volume and the density and the molar mass, whatever, to eventually get to moles, okay? Delta U, so what's the relationship for delta U for phase changes or chemical reactions? Right, I mean, often we have the relationship between delta H and delta U. Delta H equals delta U, right? Yeah, right. And so in this case, be delta H minus RT delta NG. Okay. Right, which delta NG is basically just going to be negative. Oh no, finalized. So it's just going to be N, right? Because initially your moles here are you know, of gas are 0, right? So delta NG is just going to be N. And then let's say work. How would I get work? Yep. Yep. So your work is going to be what for this phase change? Have something done in lab in just an open container. It's P external delta V, right? So in the problem, I should do this to people on Zoom see it, right? In the problem, right, told that it's boiled under 1 atmospheric pressure, right? So it's in some open container where there's a constant external pressure of 1 atmosphere, okay? So the work done by the gas is just minus P external delta V. Now, again, often we think of this equation as like I have a constant number of moles and I change the volume to, right, of those moles, right, by changing the pressure of the gas or the temperature of the gas to get that volume change, right, to get this minus P external delta V, okay? Well, in this case, right, the volume's changing again of your gas, but it's changing because the number of moles of gas is changing, okay? So, but it's this exact same thing, right? That it doesn't matter how that volume changed, why the volume changed, just that it changed, right? And so that volume change, right, is from your initial volume, which was 100 milliliters, to the final volume of that gas, okay, which you can calculate using your ideal gas law, okay, right? And that can give you your work. And then Q here, right, you can get from delta U minus work, which which will basically just equal delta H. So essentially just equal delta H. In this case, because the pressure of your gas is in mechanical equilibrium with the external pressure of always 1 atmosphere, and you have a constant external pressure, okay, for this process. And so work or heat should equal the enthalpy change. So questions about this? Yeah.
How would you use the ideal gas law to find?
So the initial volume is the 100 milliliters of the liquid, right? In the final volume, we have 1 atmosphere, whatever the volume is of the gas, equaling the number of moles of the gas that's formed, right? 0.08206. And the temperature here is 373 Kelvin, okay? Right, the N here, right, you get from the volume of the liquid and its density and its molar mass to get the total number of moles in that volume. And that's right, and after everything's been boiled off, right, that's the total number of moles you have as gas. So you just plug in that number of moles and you can solve for the final volume. Yeah, that was mistyped. It should be 373. Yeah. So no, that was a mistake. It should be 373. The entire problem is done at 100 degrees Celsius. Yeah, it's done at a constant temperature of 100 degrees Celsius. That was just a typo on my part.
And you said delta NG, which is weekend.
Yeah. Yep. All right. Okay, so final problem talk about here. Go to this one here. Nope. No, this one. Okay. All right. So we're given some equation of state of the gas, okay, and we know, right, Cp minus Cv is related to this set of kind of derivatives, okay, which is related with alpha, the expansion coefficient, isothermal coefficient of T, right? But here I'm just writing it in terms of derivatives, and then in the problem it's saying, like, given this equation of state of your gas, what is Cp minus Cv for this gas? Okay. A here is just a constant, by the way. Right? So we're given that equation of state of our gas and basically asked to solve for Cp minus Cv. Okay? So what do I need to do to solve for Cp minus Cv? Yeah, well, so we will want to solve for volume, right? First, we want to find volume. It's a function of temperature, pressure, and number of moles, right? Which is just to multiply V over, divide by pressure, right? Get that equation right. And then I want to solve for these derivatives, right? I then want to know, okay, well, what is dV dt, right? That's what that is, right? dV dt, right? What is that? What is the temperature derivative of this expression, right? That's just d dt of nRT e to minus ART over P divided by P, okay? Right? And so it's just a temperature derivative of that function of temperature here, right? Which not going to be the most nice looking thing, but nRT, nR over P e to the minus ART over P minus, n times A R squared over P squared T minus ART over P. Okay. So that would be what dV dt is. Okay. And then you could do the same thing for dP dt, right? dP dt. Right. Right. It's just the derivative of, oh, sorry, dV dP. My apologies, right? Looking for dV dP. So you need to take the pressure derivative of the volume. Okay. You'll have a similar type of thing, minus nRT over P squared, e minus ART over P. And that's going to be plus NAR squared T squared over P squared. Oh, P cubed. Minus ART of P. Now these derivatives are like, you wouldn't be getting an equation of state like this on an exam, but you know, I just picked a random kind of equation of state that has no physical meaning whatsoever. It was made up by me, okay, to kind of emphasize, right, that to solve something like this, right, in a problem where you're asked to find, say, Cp minus Cv is defined like this, or let's say I'm asked, what is alpha, right? Like what was on the homework, right? Which is dV dt, right? I need to solve for these derivatives, right? And so I have to solve for those derivatives and then plug in the expression here to simplify, which again, for this problem is not necessarily so simple. And you have your temperature and pressure derivatives. If you plug all those things in, you'll kind of simplify to something like this. Okay? ART divided P minus 1 times 4y. So again, it's not necessarily the most straightforward math problem on this here, okay? But again, you wouldn't necessarily be given something like this on the exam in terms of that type of equation of state. But I just wanted to kind of remind ourselves of this problem, right? That again, in this class, often, right, we have these different variables that we can think of as functions of other things, and then we can take the derivative of those things, right? Like solving for that dV dt and dV dP. Okay. All right. So if people have further questions, I'm happy to answer them, but otherwise we are out of time for class. Okay. Please turn in your homework. You can either turn it up here or put it on the back table as you leave. Either one, fine by me. Okay. Right. For those who are here on Zoom, make sure to submit your homework if it hasn't closed already, and if it just closed or something like that and you haven't submitted it, you can shoot me an email about it, but
Did you happen to bring the homeworks that we turned in?
today was the first day I left it in my office. So I have it in my office. If you want, I'm going right there right after class. You can follow me and pick it up.
Okay, that's fine.
Oh, I am the only one here on Zoom, so everyone left. So I'm ending.